at Advanced Research Computing. Today, I have my colleagues here. We have Jeff Gardner, Cloud Specialist, Wade Claver, System Administrator, Michael Tan, Cloud Analyst, and Gabe Smith, System Analyst. They will be here to help facilitate questions. I'd like to start my presentation by acknowledging the land. University of British Columbia, Point Grey campus is located on the traditional, ancestral, and unceded territory of the Musqueam people. University of British Columbia, Okanagan campus is located on the unceded territory of the Sioux peoples. Here are some housekeeping items. You have been muted already when you enter the room. This webinar is being recorded. The recording will be posted on the UBC Advanced Research Computing YouTube channel. Please use the Q&A option to ask questions. Questions will be answered either live or in the chat. There will be 2 5-minute breaks during the workshop. There will be a short survey appearing in your browser as soon as the webinar ends. So please feel free to leave your comments or suggestions. Here are the learning objectives. By coming out of this virtual classroom, you should be able to describe what a database is and how it can benefit your research. You can identify the different approaches to host your database. You can define the key elements of a relational database. You can build a relational database and start interacting with it. And you can perform in database analytics within a relational database. And this course has 2 parts. In part A, I will introduce some basic concepts, and you will learn what a database is, why database is important, and how to host and where to host your database. I'm going to compare SQL and NoSQL databases, so you will have a better idea which one to pick for your own research. And finally, I'm going to introduce some important elements or concepts of a SQL database. Then we're going to have a 5-minute break. Coming back, we will move on to our case study. You will be given a scenario and a list of tasks to complete. There's no hands-on or any sort of follow-up activities on your own computer. I will walk you through the questions and review the answers. We will build a database together, and we will manage and create our users. We're going to add some security to our database, and we're going to interact with our database. Finally, you will have some idea about how to perform in database analytics using this database we will be building. So, first thing first, what is a database? I have 3 definitions here from Wikipedia, Oracle, and Microsoft. Here is the thing that is in common. Database is an organized collection of data. So within a database, you have organized the data in some way, either in the format of tables, or in key value pair, or graph, etc. My personal preference is a Microsoft's definition because it tells you not only what it is, but also what it does. It makes it easier to manage and access your data. So, database is an organized collection of data that allows for easy access, management, and utilization of data. So that allows you to query your tables, your data, allows you to update your records, and it allows you to use your data either through a web application or some other things. Why database is important? Well, we are in the age of abundance. Data is coming in from everywhere. We have CSV files, we have a real-time instrument, We have web applications. Some data source may contain data that is incomplete or out of date or lack of quality control. If you use the incorrect source of data, you're going to have bad results. But with a database, you can integrate your data into that single place and to have your database to serve as a single source of truth. So within organization, everyone will be talking to the same data set, will be using the same data set, and that is a very cool thing. With a database, it makes it easy to search, filter, merge, join your tables. So that makes your data searchable. And database would allow granular access control. In this example, you can give this blue man write access to your data, the green person read-only power, and this blue one database administrator. So this blue guy will sit on top and oversee everything. And finally, with a database, you can do something like in-database analytics, which is a technology that allows you to process your data inside your database by moving into your analytic algorithm into the database. By doing so, you can eliminate the effort and the time that are required to move your data back and forth between the database and a separate analytics application. So where to host your database? I have 4 options here. First of all, you can use your private computer or a separate computer that sits in the corner of your lab to serve as a host. And it is free of charge, but you may have issues with performance and scalability in the long term. In addition, you don't want people to talk to or to go inside your computer, so sharing is always challenging. If you are UBC affiliated, there is a service called UBC EduCloud you can use. UBC EduCloud server sits on the campus, so for whatever reason, your data must stay on campus. It cannot go elsewhere. This will be the right option for you. It is very inexpensive. You get technical support from UBC IT. But there is a downside. When you first contact UBC IT, and they probably will give you an EduCloud console. So within the console, you will provision a VM, and then you will install your database server inside the VM. So you will be using the VM to host your database. And we also have Alliances cluster or cloud resources you can use for hosting your database. There are many clusters, and I will talk about that later on, but these 3 clusters, Arbutus, Cedar, and Gram, can be used to host your database. And it is also free of charge. You get technical support from Alliance Group. And Alliance previously is called Compute Canada, by the way. And you've got to apply for it. And not too many people like forms. And you have to be a principal investigator. If you are not a PI, you've got to talk nicely to your boss and ask him or her to put the application through. Once approved, you can be added as a user to that allocation. Commercial cloud. Amazon, Microsoft, and Google are the big 3 commercial cloud providers. They have excellent performance and scalability, and they offer comprehensive support, but it costs money. If you don't understand their pricing model very well, don't be surprised to see a huge bill. Now, let's compare SQL and NoSQL. Those are two types of databases. SQL is referred to as a relational database. So within SQL database, your data objects are related to each other. But there's no such relationship in NoSQL, and that's why it's called non-relational. It can also be called not only relational. The reason of that is that NoSQL can handle structured, semi-structured, and non-structured data. Here are some examples of commonly used SQL and the NoSQL databases. And some of them may look quite familiar, but some of them may not. Cassandra, for example. Use cases. Both SQL and the NoSQL databases are heavily used for web development and mobile applications. SQL is widely used for data mart and data warehouse, while NoSQL is heavily used in gaming industry and social media. So for scientific research, SQL has been used for many decades because it's classic database, right? And it's been around for about 50 years. But recently, people started paying more attention to NoSQL database, and people realized NoSQL database is also a very important tool to support scientific research. I have links to 3 research papers. So if you like, you can read these papers to understand the importance of NoSQL in support of scientific research projects. Database structure. So for SQL database, the data in the database is in the form of a series of tables. And the tables are linked to each other. But this is not the case for NoSQL. There are 4 main categories of databases in NoSQL. And this key value pair database is similar to SQL. It has unique identifiers that uniquely identify the records or the rows within a table. But the value component is more complex. It can have a string, it can have a numbers, it can have even JSON file or combination. But in SQL, you got to be either having a number or string. You just cannot mix them up. Column-based database is similar to key value pair. Instead of having value, it has columns component. Within each of the columns, you can have rows and columns. The rows and the columns in one column do not have to match the rows and the columns in another column. It is wordy, I know, but it's just the way it is. Next one, document-oriented database, is also similar to key value pair. Instead of having values, your data will be stored as documents in the format of XML and JSON. And this graph-based database is pretty self-explanatory. Your data will be stored as graphs. Schema. So schema, I have a separate slide talking about schema, but what schema is? Schema is a blueprint of how your data is organized. And within a SQL database, you have a static schema. That means the elements in this schema will not change. In this example, I have 1, 2, 3, 4, 5, 6 tables, and within each of the tables, there are data fields. So by static, I mean I always have these 6 tables, and within each of the tables, I won't delete any of this data field. Or there will be a change to my schema, but such change will not happen very often. But for NoSQL, it's a different story. Today, I can remove these 2 data objects, and tomorrow I can remove this guy, and the day after tomorrow, I can bring new one in. So I have a dynamic schema for NoSQL, or there's no schema at all. Scalability. SQL database can be scaled vertically by adding more RAMs, more CPUs, and a storage. It's just like a wedding cake. You can keep adding layers on top of the other until you reach a certain level. When you hit the cap, you cannot scale your SQL database anymore. So that is the downside. But for NoSQL, it's different. You can scale your database vertically, just like this SQL, by adding more RAM, CPUs, and storage. At the same time, you can scale your database horizontally by adding another database cluster or node to the existing one to form a distributed system. So that's one of the real beauties with NoSQL. Querying. Querying SQL database is easy and straightforward, and there is a standard syntax for doing that. In this example, I am requesting everything, all the data in this customers table, where favorite website is techonthenet.com, and I want to order my results by last name in ascending order. And I hit enter, and this is what I get. So this table had this query returns 2 rows with favorite website is techonthenet.com, and my result is ordered by last name in ascending order. And for NoSQL, there's no such standard syntax for doing that, but this is still doable. It's just you have to deal with that case by case. So which one to pick for your own research, SQL or NoSQL? I would say it depends on what sort of data you have, what kind of schema do you have, and how you want to use your data. If you have a structured data, and for example, your data is coming in standardized format, always binary format, always CSV, always video, and you can well define your data in a series of tables in the format of rows and columns. And if you have a static schema, the elements, the tables fields in a schema do not change or do not change too often. And if you want to do a frequent manual queries, yes, SQL is the option for you. And if you have unstructured data, and if you have a dynamic schema is changing all the time, or there's no schema, and if you have a big data applications, for example, you have some sort of plotting utility that will plot out your data by specifying the date range, or you have a forecasting algorithm, and I would recommend NoSQL. Next, I am going to focus on SQL databases because SQL database has been around for about 50 years. It's classic database. Everything is very well organized in the database, and it is user-friendly. And so I have 3 tables here: course, faculty, and a student. It's just like Excel. You have rows, sometimes called tuples. You have columns or fields. and you can pull data from different tables to form something called records. The lower bottom table, and you see there are 3 colors. The blue one is from student table. The green is from faculty, and the course name, which is red, is from course. So what I did here is to grab different data fields from different tables and put them together to form a record or data record. Same tables again. So within each of the tables, there is a data field that uniquely identifies each of the rows within each of the tables. They are called primary keys. So primary keys are unique identifiers. Looking at this course table as example, if I specify course ID equals 3, then the database knows I'm talking about this row. That's primary key. And we also have a foreign key or linking key. Foreign key is a very important concept, and that links one table to another. In this example, student table is linked to course table through this course ID. And student table is linked to faculty table via faculty ID. So foreign key is very important, and it makes like a network. It links one table to another, forming a network. The next concept is data type. What is a data type? Data type is a description of the format of data. In computer science, each variable must have a data type. Without a data type, the computer just wouldn't know how to store the data. What I have here is some commonly used data types and the syntax you would use when you develop your database. What I want to say here is that the syntax can be different if you choose different databases. For example, if I have an integer data and I would specify int for SQL Server and number if I'm using Oracle, and it's going to be either int or integer for MySQL or Postgres. Schema. Schema is a very, very important concept of a SQL database. What is a schema? Schema is a layout or representation of how your database is constructed. So a schema must contain some elements. In this example, this schema has 3 tables, and it has some data columns or data fields within each of the tables. It has data types to go with the data fields. It has primary keys that uniquely identify each rows within each of the tables. And it has foreign keys that link one table to another. So this is a schema. It's like a diagram. Then we have something called an ER diagram. So ER diagram is a diagram that shows how entities within each tables are related, if any. In this example, student table is linked to course table through this course ID. And the student table is linked to faculty table via this faculty ID. As you can see, I have some symbols here at each end of the relationships, and they are called crow's foot notation. There are 1 or 0, 1 and only 1, 0 or many, 1 to many relationships. And we're going to take a close look at that. We'll focus on the student and the course tables first. We start from the left side. So one student can have a 0 course because he had enough and he decided to take a year out. So he didn't register any. But when he came back next year, he feels great. So he enrolled to multiple courses. And that's why you're seeing this 0 to many relationship. On the other hand, one course can have no student because it's a difficult course. You are told not to do it by your friends. And one course can have many students. And that's this 0 to many means. Then for student and faculty tables, one student corresponds to one and only one faculty. And one faculty can have one or many students. So these are the cross-foot notation. So don't get yourself confused between database schema and the ER diagram. Database schema is a layout of how your data is organized, and the ERD shows you the relationships between entities. Okay, so after the break, we are going to do the case study. But before we go to the break, and do we have any questions? No? Okay, we're doing good. So let's do a 5 minutes break and we'll come back at 10:05. We have one.
Sorry, I didn't realize I would close the question. I'll just answer this one live. Typically, when you're sharding databases in a NoSQL scenario, that's done to distribute the search and query workload over multiple servers in sort of, think like a Hadoop style workload. In a SQL database, it's a little bit more difficult to do because you need to make sure that you're always maintaining some sort of relational integrity. So we can't do things like be updating a record on one server while we're querying it on another server. We could get different values than what should be there. So typically, if you see a database spread across multiple servers, that tends to be in service of increasing read performance. So you would have some sort of load balancer in front of it, and you would be doing read-only queries of a database system, and it would maybe dispatch those queries to different databases, which are mirrors of each other, just in order to to hit some volume of queries per second that wouldn't be possible with a single server. Does that answer your question? Just indicate in chat, I guess. Okay.
Okay, so we're moving on to our case study. This is our scenario. There are 3 sites, Venus, Mars, and SOL2. At site Venus, which is a marine protected area, we have an O2 oxygen sensor deployed, collecting oxygen data. At site Mars, which is a salmon farming site, there is a nitrate sensor deployed, collecting nitrate concentration. Autonomous just means the instruments are running on batteries, collecting data at a predetermined interval. And this site, SOL2, is a natural wetland. It doesn't have anything installed at the moment, but it may get something in the future. So all the sites have coordinates. And we also know the instrument's name and also vendor's website. Here are the tasks. Task 1, you will create a database to store all the data and the metadata. Task 2, you will query your database. And task 3, you will merge, join, and sort your data. And task 4, you will do some basic in-database analytics, i.e. linear regression and response prediction. So I'm going to start with task 1. And I will break this down into 8 steps, starting from deciding SQL or NoSQL, all the way up to creating the table. Step 1, SQL or NoSQL. Remember, it depends on what kind of data you have, what type of schemas you have, and how you want to use your data. Let's go back to our scenario a little bit. Looking at this scenario, it seems to me it talks about 4 things. It talks about device, it talks about sites, O2 concentration, and NO3 concentration. 4 things. So feels like I can have 4 data objects to store the data and metadata. The object device can be used to store device name and vendor information. Site name, site coordinates, and site description can go to the site object. Oxygen and the nitrate objects can be used to store concentration and the timestamp when the concentration was taken, and also unit of measure. Each object can have their own device, own data fields and the data type. This SOL2 site doesn't have anything at the moment, but it may get a new device, or it may get a third device in the future. But this is not going to change the structure of our data object. You're still going to have the same data fields. All you will have is a new record under device name. For example, phosphate data logger, and a description to the new vendor's website. Oxygen data and the nitrate data are in binary format, and it's consistent. And I read the instrument manual, and this is the raw data stream. The raw data comes in every 15 minutes and in standard format. Now I know I have a structured data. Do I have a static schema or dynamic schema? This is my schema. My schema will have 4 tables or 4 objects, and each of the objects will have data fields and the data type. The data fields will not change, and the data type are going to stay the same. So I have a static schema. Do I need to manually query my data? Yes, I do. And at the moment, I don't have any separate applications to read the data. So it's pretty clear now. Relational database is the option. Here are the candidates, and I will go for Postgres. There's nothing wrong if you use MySQL or Maria database or Oracle. This is just a personal preference. Step 2, design schema. Once again, schema is a layout of showing how your data is organized. A schema must contain some elements. This is my schema, which is called training 1. In my schema, I have 4 tables, and I call them previously objects. Then I have primary keys within each of the tables, which uniquely identify each rows within each of the tables. I have foreign keys that link one table to another. For example, device table is linked to site table through this site ID foreign key. And I have data fields or data columns. And I have a data type to go with a data field. I want to say something about this reading here in this oxygen table. The reading gets numeric data type, but with 5,3. What's that? 5 is a precision. That means this numeric data value allows the maximum digit of 5. And 3 is a scale, and that is the maximum digit in the fraction. Unit, varchar 10. So I use varchar 10 to allow unit to store various characters that are up to 10. So anything less than 10, you don't have issues. Anything above 10, you will get a complaint. Then I can move on to this ER diagram. Once again, ER diagram is to show the relationships between your entities. And we're gonna use this cross-foot notation to add the symbols on both ends of our relationships. We're gonna do the device and the site first. One device can have no site because that device is not installed. It's sitting in the shelf of your lab. And once that is installed, one device gets only one site. So that's why I say 0 to 1 relationship. On the other hand, one site can have no device because that's the case for SOL2 or just one device. Now we move on to device and oxygen tables. One device can have no oxygen data because the instrument was turned off for maintenance, for example. Once turned on, it can have many data. So that's why you see this 0 to many relationship. And one oxygen corresponds to one and only one device because we only have one oxygen device across the sites. Similarly, we can add this 0 to many relationship to this device to nitrate relationship, and one nitrate can it's only corresponds to one and only one device. Once again, don't get yourself confused between database schema and entity relationship diagram. Schema shows you how your data is organized or constructed, and the ER diagram just shows you the relationships between the entities. Step 3, hosting my database. I am going to use Alliances cluster to host my database. There are 6 clusters. Arbutus is a cloud site. You can provision your own customized virtual machine. Niagara is meant for running large parallel jobs. The rest are general purpose clusters. If you want to know more about Alliances clusters, this is the documentation. I could go for Cedar or Gram because they have a Postgres database server installed already. But I think I'm okay with managing and installing the server myself. So I will go for Arbutus. Next question, what sort of virtual machine do I want? I think I like Ubuntu operating system, 4 CPUs, 8 gigabytes of RAM, and 500 gigabytes of storage. And you may ask the question, hey, I don't know how many CPUs I want. I don't know how many RAMs I want. I don't have any idea. I would recommend you start with this 4 CPUs and 8 gigabytes of RAM, and that should be sufficient enough for your project. And in the future, if you find your virtual machine is running slow, you can contact the Alliances team and ask them to bump up your VM. There's no issue at all. Just in case you wonder what is the minimum hardware requirement for running Postgres, here you go. It only requests 1 gigahertz processor, 2 gigs of RAM, and a 512 megabyte storage. So I know what I want. Now, then I wrote an email to Alliance's cloud team, and they did something behind the scene, and they got back to me with this documentation. And this is a good document. It tells me how to provision a VM, how to create a SSH key pair, how to set up my network and the security, and finally, how to connect to my VM. Then I followed the instructions, and I used OpenStack to provision a VM, my own VM for this project. Then when I had my VM, I just log into my VM using this command. I will talk about this command on the next slide. And then I installed Postgres database server using this sudo command. Step 4, creating database. I will create this database inside the VM. So I need to log onto the VM first. And I use this command, SSH command. CC key is the name of my private key file. And you can use the Alliance's documentation to help you create your private key and public key file. And Ubuntu is the default login name. If you are using CentOS for operating system, you will specify CentOS instead. And you need to enter the IP of your VM. You hit enter, and then you're inside your VM. And the VM, this ML is the name of my VM. Then I just use this sudo command to create my database. And you've got to specify the owner of the database. In this case, it's Postgres. And the name of your database, training. Now we have our Postgres database called training. You can verify your database, but first you need to log into your VM, and then you can connect to your database using this sudo command. So Postgres is the username you are trying to connect, as PSQL is the terminal for interacting with Postgres, and the training is the name of the database. You hit enter, and you are inside your database. And you will notice that because your prompt changed. You can use DT command to list all the tables within this specific database. We don't have any tables built yet, so that's the reason you see did not find any relations. Relations just mean tables. Step 5, create schema. We are going to create a schema inside this database training and call this schema training 1 and use this schema as a basket to collect our data. And this is simple. And this is a command. And you can verify your schema. It's here. So let me put a little pause here and ask you, am I losing you? Yes, no? Yes is the correct answer, because I talked about servers, I talked about clusters, schema, database. So let me explain what I did. First, I targeted Abuda's cluster. And then I built a VM inside Abuda's cluster. And I have a database called training inside the VM. I just created my schema training 1 to work as a basket to collect my data, which will be in the format of a series of tables. And please know this schema is not necessary. And you can have all of your data to go directly under your database. But the reason of having schema is that when you have a large data set or too many tables, and you could categorize different types of data into different schema, and to have your web applications, for example, to read the data within a specific schema. So I'd like to use schema to keep my items tidy. And if you do not want to have a schema, it's fine, and you just forget about this step. Next step, create users. I have 3 users, Trainer, John Rambo, and Peter Pan. They want to have access to the data. So first of all, I create these users, and I must do that within the database and with password for sure. And then I give them access to the database cluster using this command. After that, I give them access to this specific database training I just made. So they can connect to this database. And then I give them access to the schema, because the schema will be used to store my data. Next, I give them some privileges to the database, schema, and tables. And don't get confused by these all privileges. It doesn't mean all the privileges. And so they could connect, they could create temporary tables or stuff like that. And then I give them a select, insert, update, and delete privileges to all tables in this schema so that they can interact with the tables. Trainer asks for super user's role, and this person knows what he's doing. So I made him a super user. Finally, I can use du command to list all of my users with their privileges. This is a summary of what I did here. First of all, I created my users, and then I give them access to the database cluster. Then I give them access to this specific database, then access to the schema. Finally, I give them some privileges so that they can interact with the tables. Step 7, logging to database. Before a user can log into database, there are something you need to do. You've got to update this Postgres configuration file. And every time when you connect to Postgres database, this file will be read. If the user is not specified in that file, Postgres is going to barf. How to do that is easy. You connect to your virtual machine first, and then you open this file, pg_hba.com. Depending on the version of your Postgres and your operating system, mine is here. And what you need to do is to add these 3 lines to this file. Training is the name of my database. These are my users. And I need to specify the Postgres IP. And this 32 is just 0 notation. That means only this specific IP is accepted. MP5 just means when the user connects to the database, he or she must enter the password. Then I'll restart the Postgres server. Next, This user must have access to the remote Linux machine, the VM, because this database is installed inside the VM. How to do that? First, you need to log into the virtual machine. And then you make home directory using John Rambo as example. And then you add this user, John Rambo's public key to this file. I added trainer to the sudo group. So be careful when you want to add someone to the sudo group, because a sudo can bypass lots of privilege checks, can actually do harms to your system. So you don't give people sudo privileges unless you really have to, and that person knows what he's doing. And finally, I set the user permission. 700 means only John Rambo can access this directory. There are more user permission settings. This is the documentation you can read about. Then my users can log into the database. Postgres is a database administrator, is also a sudo. Trainer is a sudo, so they use this sudo command to connect to the Postgres. And they both need to enter their password. And John Rambo and Peter Pan, they are non-sudoers, so they will use this PSQL command to connect to the database. They've got to specify the host IP and then same database name and enter their password. So my users are sort of happy. Why not 100% happy? If you recall, when I made these users, I gave them temporary passwords. They haven't really had a chance to update their initial passwords yet. How to do that? It's simple. I'm using trainer as example. So I log into the database, the VM as trainer, and then I connect to the database as a trainer. Finally, I change my password. That's it. Now, all my users are happy. Step 8, final step, create tables. I will bring my diagram to help me preparing the syntax for creating the tables. The rule is that you always start with the table that has no foreign keys. In this example, site tables. This is my syntax. So I will create my table called a site, and this table is under schema training 1. And this table has 1, 2, 3, 4, 5 columns or fields. Each of them has its own data type. Site ID is the primary key, which will uniquely identify the records within this table. So it gets serial data type. And I specified not now for site name, longitude, and latitude. This means when I insert a data or a row of data or batches of data into this site table, I must specify the site name and the coordinates. They cannot be empty. Then I move on to device table. I couldn't start with oxygen or nitrate. Do you know why? The reason is this field. If I'm doing oxygen table next, I will have a field called device ID, and that device ID refers to this table. Since I don't have this table yet, so Postgres is not going to be happy. And that's the reason I handle this device table next. Similarly, I will create my device table within schema training 1. And it has 1, 2, 3, 4, these 4 fields. And this is my primary key. Site ID is not null. You must specify device name when you insert some data to this device table, which makes sense, right? If you're inserting something you don't know, that's not going to work. And what I want to say here is this line. Since this table has a foreign key site ID, and you will say something like, this table has a foreign key, that is site ID, and this foreign key references site table under training 1 schema within this site table, and it's called site ID as well. So that's what this line does. This line creates a foreign key entity, and that will link this device table to the site table. And then it doesn't really matter if you do oxygen first or nitrate first. I'm just gonna work on the oxygen. And same thing again, oxygen table under training 1 schema, and this has more fields. And for each of the field, I have to specify the data type. And some of the fields must have data, but some fields are okay. And in this table, I have a device ID field, and that field is a foreign key. And this foreign key references device table, device ID field. That's this one. And similarly, you can prepare the syntax for generating nitrate tables. And if you don't want to include your schema, then it's fine. Just delete that from your syntax. The important thing here, as you can see, always use your diagram or the layout of your data to help prepare your syntax. And you can run this syntax in a shell or in an IDE. I'm going to talk about IDE in a minute. And task 1 is half done. Why? Because we only prepared the syntax here. We haven't really run the syntax yet, so we still don't have the table. And this will be handled after coming back from the break. Okay, how are we doing with the questions?
I'll apologize if my questions in chat are long-winded, but some of them are really good questions. Keep them coming.
Okay, cool. Thanks, guys. It's 10:37, and we have a bit of time, and let's come back in 5 minutes. 10:42. I just want to say something regarding Martin Chan's question. You're talking about using MS Access, and that is an option, and also you can use SQLite. So that doesn't require any sort of like a messy interaction with the database or with the server. It's just like a file system. But there are some downside with using MS Access or SQLite because it doesn't support multiple users. So if you are updating it and somebody else will not be able to update it or not even, they can read it. And so that would be an option.
Yeah, I did supply some fairly lengthy remarks on that one. The one thing I will say is, you know what, if you like the tool and that drag and drop interface for, developing entity relationship diagrams and sort of defining the layout of the database, if that's a tool that you really like to use, that's great, it works. You just might want to take those tables that you design and that database you design there and take some of the sort of SQL skills that you're learning here today and port that into something that's a little bit better suited to, offering out to the world via network.
Yeah, that's right. So we're not saying SQLite or MS Access are not great. They are great, and depending on what you want to use them, and certainly they have some disadvantages. And so with a relational database, Postgres, for example, or MySQL, and although it looks like there are some settings you need to do, but once everything is set up properly, you will really love it because you can join tables, you can merge them together, you can play away with them, and you can just download your data output locally or download it, put it on your remote machine. So it's all sort of things. Right. So I'm going to move on to the final part. Just before I start, there is something I'd like to say about cybersecurity. If you recall, we use SSH command to log into our virtual machine and talk to our system. And by doing so, your communication will be encrypted. But if you are still feeling a bit nervous, there's something else, or there's extra security layers you can put on both your VM and your database. Let's talk about the VM first. Alliance has a nice documentation here, and it talks about something like you should update your VM regularly. You must not bundle ranges of ports to allow to access. And for people from outside of your organization, they don't even need to know there's a Postgres database existing. They will be using something else, or API, or a web application to access or to make use or to see your data and more. There's also IP table you can use to manage the traffic. IP table is a Linux firewall. It's command line firewall. It uses a policy chain to allow or block traffic. This is the documentation. You can read more about IP tables. It's a great tool. Here's an example. If you want to block access from this IP, it's simple. On the other hand, for Postgres database, you should read the Postgres documentation, the security chapter. It tells you more about security concerns. or considerations. DigitalOcean has a nice document here, and you definitely want to read that to know more about their security considerations against this Postgres database or and attacks. And when you create your user, you always want to use a password, give them initial password. And there's something I want to say here. When your database server was installed, you will have your user Postgres installed automatically. And depending on your Postgres version, this user may not have a password or just use Postgres as its password. You must update the password here to something else. And finally, you can consider SSL connection, which is a secure sockets layer connection. And if you use SSL connection, then your communication with Postgres database will be encrypted. Just by default, this SSL is not turned on, but it's in the Postgres configuration file, and this is a bit of advanced level, and this will not be covered in today's presentation. And if you want to know more about it, this is the document you want to read. So you can add additional security layers to both your VM and your database. Then you should feel secure. Task 2, query the database, and task 3, just doing some data manipulation. You can do these in a shell or IDE, and I'm gonna do this in IDE. What is IDE? You heard me talking about this a few times. IDE is called a Database Integrated Development Environment. That is a web-based GUI tool, which can be used to interact with databases both locally and remotely. So it's a GUI. Specifically, one IDE can be used to create tables, create databases, create functions, triggers, sequences, and so on. You can use IDE to interact with your data because it looks much nicer rather than black and white screen. And you can manage users. You can grant user specific privilege in IDE. And you can also monitor traffic. And there are more things you can do. Excuse me. I have listed some examples of IDE. These 3 are free of charge, and this is paid. And I'm going to use pgadmin for the demonstration. And what I have here is a screenshot of pgadmin instance. In this plot, you will see we have this menu bar. We have a browser from which you can select your schema, database, or tables to work with. And you prepare your SQL syntax in this editor. Once executed, your data output will be displayed in here. So now I'm going to reorganize my screen, and I'm going to have this presentation on the left-hand side, have pgadmin on the right. Okay, I hope everyone can see my new screen. And now we're gonna continue with task 1. And at this step, so far we only have our syntax prepared. We haven't actually run our syntax yet, and I'm gonna do that in pgadmin GUI. So from the left pane, as you can see, I'm connected to this CCML virtual machine, and underneath I have 3 databases. I am using training 1 database for this presentation, and I have a schema called training 1. Within this schema, I should have tables because it's not connected. My connection is broken. Sorry, I need to reconnect. Right, so and we shouldn't have anything here. Yeah, because we haven't created our tables yet. And this is the syntax you have seen earlier. So same thing, I just run these lines and done. And the next one, now if you refresh that, you will see your tables. And next step, we are going to insert some values to the tables. We're going to start with a site table. This is the syntax we will use because we have 3 sites. And that's the reason we need 3 inserts. So we will insert some value into this site table, and this site table is under training 1 schema, and my values are in the brackets. The important thing here is that the order of your values in the parentheses must follow the order in the tables. For example, in this site table, the first value is site ID. That is primary key, which will automatically increment. And I use default for primary key. And the next element is site name. That's this one. And third, fourth, longitude, latitude, and the site name description. So that's just for inserting this Venus site, and I will run this command. Done. Then I'll move on to my device table. This is the syntax I use. I have 2 inserts here because I have 2 devices. And I will insert something into this device table with values in parentheses. And remember, the order in the values must agree with the order in this table. The first element is device ID, and that is primary key. So I don't have to specify the number. I can just use default. And you could say something like 56, but it's good to use default because it's going to use the next available number that is not used in the table. And then the next element is site ID. Site ID, then I will refer to this site table. And this is site ID 1 because that's the first insert. This is site ID 2. So I will put this oxygen sensor at site 1. That's Venus. And this nitrate sensor will be installed at site 2. And also I included the vendor website. I will run these 2 lines. Now I'm going to handle the oxygen table. I'm going to insert 12 lines here. I'm not going to go deep into this syntax again. It just reminds you The order in the brackets must follow the order they appear in the table. And this is my reading time format, and because it's like it's not a number, right? It's got this hyphen thing, so it must be quoted. And I don't have to put it in quote, to be honest, but it's okay. And this is my unit of measure that corresponds to this component. And description, I didn't worry about any description when inserting this oxygen data and nitrate data. These are just plugging numbers. So now we have our tables and we have our records in tables. Task 1 is done. Task 2, let's query our database. Let's read what's in our table. This command is going to grab everything. Star means all the fields that is in this device table under training 1. If you don't have a schema, you just drop this part. We'll run this command. This is what we have. This table has 4 fields. This device name and the vendor's website. And this primary key that is generated automatically, the site ID. And if you don't want to see all of the columns, you don't have to use a star. You can specify the columns you want to see. In this case, we just want device ID and device name. So you specify these 2 columns and you get a lighter table. So similarly, we can query our site table. We have 3 sites. We just made the 3 sites. This site is a natural wetland. It doesn't have anything installed. Our oxygen table. And our nitrate table. Okay. Next, update records. Quite often, we need to update our existing records or rows or data. For example, if we found a typo or something needs to be updated. And let's look at this device table, for example. This looks okay, but what if I want to change this device name to something else? And I use this command. So I will update this device table. This table is in training 1 schema, and I set this field to something else where device ID is 1. That's this one. That's why we need this primary key, because every time when I specify device ID equals 1, Postgres knows I'm talking about this line of data. And I run that. Done. Let's see the changes. It's called unknown now. You can always put it back. So this is updating existing records. Delete records. You don't need to do that too often though, because you could use the description or notes or comments section to note anything that is important. We use this site table as example. This site, because it doesn't have anything, and half a year later, we decided not to worry about this site anymore. So this site can go away from the site table. So we use this command. We delete from this site table this entire row, but we only need to specify this primary key. That's what it says here, where site ID equals 3. We will execute this line and we select all the items in the table again, and it's gone. I'll put it back for now. It's back. So task 2 is done. And I'd like to put a pause again here because some of you may think, hey, there are really lots of settings to the VM, settings to the database, and a lot of syntax. I'm not very comfortable with that, and I don't want to do that. And it goes like this. And why I cannot use Excel? Because that's easy and simple. Now, task 3 is going to show you the real beauty of having this relational database. First of all, join tables. And let's look at our oxygen table. So this syntax is slightly different from the one you saw earlier. So earlier you just have this one, select everything from oxygen table. But this one, we don't want to grab all the data. We just want the data within these date ranges. And we order our data by this oxygen ID in ascending order. So that's why you're seeing fewer records here. This table looks okay, but I don't like this bit. I don't like this device ID. What I want is a real device name, right? And also the site name, the site info. This oxygen data was collected. How would I do that? Luckily, we have our foreign keys. Then we can link one table to another, and then we can join these tables. What I need to do here is to join device table and the site table with this oxygen table. These are my syntax. And I wouldn't dive deep into the syntax today because this is going to take another half an hour or so. But what I'm doing here is I am bringing this device table and the site table into my oxygen table, right? And I will be using two foreign keys. In device table, this device ID is the same thing as device ID in oxygen table. So this line 113, is going to actually bring the device table into the oxygen table. And this line is doing something similar, but it's bringing site table into this oxygen table because of this foreign key. Now, our oxygen table is not oxygen table anymore. It's a combination of 3 tables: oxygen table, device table, and the site table. And then I only want to select these columns that I am interested in. Because imagine it's better not to use a star because we have 3 tables, right? There are many rows, many columns, and I don't need that many. And the rest will be the same. Let's run these lines. Here is what we get. Now we have a proper device name, and we have a site name and coordinates to go with our data. It's not like what we saw earlier here. So you can actually join tables and to make your data records more meaningful. The next one, merge tables. Let's look at our oxygen table. Right. Normal, nothing special. And the nitrate table. It's neat too. The problem is sometimes we want to do some analysis because the data are into different tables, and that makes my life a little bit difficult. What if I can put this data into one table? Then I can work on to that thing. Yes, you can do that. And that's what it does here. Horizontal means you can bring one table. I shouldn't say bring. You could append one table right next to the other. That's what these commands do here. This is a full auto join. And so I am going to join nitrate table with this oxygen table on this field. And don't worry about this syntax here. Just today, I just would like you to understand here are the things we can do if we have a relational database. And if you think that's something you would like to try, and you can start learning this syntax. And then I only want these data fields. And I rename the fields because I read about someone was asking, can we have the same field name in different tables? And Michael provide excellent answer. And yes, if sometimes some people try to avoid it, but if you are having a really big schema with many objects in it, it's inevitable. So that's what I'm doing here. I'm going to rename this unit field as oxygen unit, and then rename unit in nitrate table as a nitrate unit. And I'm going to run these lines. And this is what I got. So on the left-hand side, I have my oxygen data, and all of these are renamed oxygen concentration. And on the right, I have my nitrate data. So now you can run analysis or regression or plot your data. Alternatively, we can put one table right beneath the other one to make it less messy. That's what this does here. This is a union command. Let me just simply run these lines and you will see what I meant. Okay, so much less messier, like I said. And from line 1 to line 12 are a oxygen data, because oxygen instrument is deployed at is the first ID, gets device ID 1, and anything beyond here is nitrate data. So by a vertical join, you can append one table right beneath the other one, making it looks better. So this is merged, and we can sort our data. This is easy. And what this command does is to select all the columns from this site table, and I order my results by site name in ascending order. And you don't have to specify ASC, because by default, your result will be sorted in ascending order. Alternatively, you can sort your data in descending order. That's what you see here. Okay, so task 3 completed. Task 4, the final task. We're gonna see how our database can be useful in supporting our in-database analytics. I am going to use Visual Studio Code, VS Code, for this demonstration. So VS Code, just like any other text editor, but that is developed by Microsoft. This can be used for Windows, Linux, or Mac. This can do many things. It can support code writing, code refactoring, debugging, and it's Git friendly and more. And you don't have to use VS Code. You can use Eclipse, Atom, or Sublime Text. Okay, what I have here is a screenshot of my VS Code instance. It has a menu bar, activity bar, from which you can connect to your remote host or remote virtual machine, and you can add new packages. In this example, I have R installed, and then we have this status bar, which tells you if you are connected or not. In this case, I'm connected to my remote host. And we have Explorer, and we can explore our repository. Code editor, you can compile your code, either Python code or R script. And when you run your code, your results will be displayed in this output panel. Okay, so let's go back to, let's get rid of this Postgres thing. And okay, this is my VS Code instance. And there is some setting you need to do to connect your VS instance to your remote server. And I'm not gonna cover that in today's presentation because it can take time, and it's not our main purpose of this presentation. And what I have here is I made a Python library called training. Let me just close this bit for now. And within this library, I have two modules. It's connect to DB. So this module is going to connect to my database. And this module will read this configuration file, which is in here. I'm not going to click on that because you guys can see my password. And this is not a special file. It's just, it looks like this. And it has a host, that's the IP of your database, and a Postgres default port, name of your database, and the user you are connecting as, and your password. And once again, I won't dive deep into this coding part, and I'm just going to go through this quickly. And first of all, you're going to verify this configuration file is there. Otherwise, it's going to give errors. And then it's going to parse this configuration file and assign the values to the parameters. And finally, it's going to return the connector you are actually used to connect to the database. And there's another module, it's a simple one as well. What it does is to grab the fields or the columns in a database table and display the fields or your results in Python pandas data frame. So it's nothing special here. Just F string. And then I made this notebook file. I do some import first. And first of all, I'd like to see what's in my device table. And that's what this code block does. Right, this is a simple one. That's my library, and that's my connector. And then I specified my schema, and I want this device table and only these three columns. And I run that. This is what I have. Same thing as you see earlier. And similarly, what's in the side table, I should have 2 records, 3, sorry, yeah, because I just put this back. And yeah, that looks right. And let's take a look at what's in our oxygen table. In this case, I specify the columns, and okay, that looks right. Right, so this is just another way showing you how you can talk to your database tables and see what you have in your table. You can use a shell, or you can use a database IDE, or use a text editor to do that. And for the in-database analytics, that's what this code block does. This code block does 4 things. It will plot the oxygen and nitrate concentration. Then it's gonna fit the data with a linear regression line and the model. Then it's gonna predict the nitrate concentration based on this model. And finally, it's gonna compare the actual concentration with the predicted concentration. And so this is the code block. Once again, it's gonna check if the connector is there. It can talk to the database, and then I specify the schema name, and I made 2 data frames. One is oxygen, the other one is nitrate. I make it bigger. And just some basic plotting here. And I'm doing some converting here. And I want to display the R-square value and other key parameters of this linear regression. And I plot the data, and I display these parameters, and then I plot the data and run it. And this is what I get. I have a plot of oxygen concentration versus nitrate. And this is the linear regression line. It's terrible, but it's okay because these 2 sites are completely separate. So you wouldn't expect there's any linear regression between the data collected from 2 completely different sites. And this is my model. R-square value, slope, and intercept. It's not great, once again. And this comparison of the actual data with the predicted nitrate concentration. And task 4 is done. So there are a lot more you can do in here. What I'm doing here is just to give you an example of what you could do with this, using this relational database. And you can do prediction, you can run multiple regression, you can do some advanced machine learning things. And that leads to the end of my presentation. And so today we talked about what database is and why database is important. And we compared SQL with NoSQL, and so that you can decide which one to use for your own research project. And then we had our case study. We build our database, and then we started interacting with our database, and finally we had some idea of how database is important in supporting in-database analytics. And there are many things I couldn't cover today. And if you have any specific questions, feel free to email me here, or you can email arc.support for more general questions. And let's see, how are we doing with the questions?
Hi, George. There was one I was going to answer in the chat there. Oh, hold on a sec.
Mm-hmm. So looks like we're finishing a bit earlier today, but so there is a very short survey, and very short, I promise. It's 2 questions. One is multiple choice question, the other is open question. So feel free to leave your comments when I terminate this training session. So
sorry, there was a question there, George. Sorry, I just had to close my window. There's a bunch of noise outside. Somebody asked about the tool you use to make the diagrams, and I'll let you speak to that in a second. But one thing I just wanted to mention, my favorite tool for designing databases is bar none, a whiteboard. It's really, it's important to keep in mind SQL is just one tool we use for managing data, but designing a really robust picture in your head of how all of your data relates is a fairly organic process. And just being able to sit there and draw blobs that represent the different types of data you have and arrows to show how they relate to one another, I find is a really useful exercise to go through it, and keeps you insulated from the technical nuts and bolts, because ultimately all of this SQL stuff and schema and all of the different pieces we use to put together an SQL database, those are sort of nitty-gritty details that really don't matter as much as having a really good picture of what your overall data model looks like, because that's what's going to influence how your data flows through your research project and influence the kind of questions you can ask of the data. So when you're drawing those pictures, that's where you can find out that maybe there's some missing piece here. You see some question that you anticipate asking that you can't draw a picture around, in which case it's really time to revisit that data model. And the time to do that is before you've spent all this effort codifying it into a SQL schema for and doing all of that work. So just something to kind of keep in mind.
Yeah, very well said, Wade. Yes, it's true. And it's all about, just transferring your ideas to a diagram and then to tables. And if you haven't handled with these kind of things before, yes, this can be overwhelming. But just please consider our case study as a very simple example, because there are not too many data objects involved, and there are less tables and not too many data fields, and the data types are quite straightforward. And I used this draw.io to do the diagram, and I found it's good tool. But there's something I dislike about is this one, because I want to draw a line, but I could do that manually, but I want this table to be splittable into multiple columns, because sometimes I want to put this data type in the table as well. And it doesn't look like it supports that, but I could be wrong. Okay, any other questions? Thank you guys for doing the questions. And yeah, I saw there are some great questions. Okay, and right, so I will terminate this presentation.